So middle of page A20 with the hyperbolas, appendix C, second half. All right, so when we talk about hyperbolas, yesterday we were talking about ellipses. The main way that we can distinguish between a hyperbola and any other of the conic sections that we work with is they're the only ones that have x squared minus y squared or y squared minus x squared. It can be in either order. So even though they're in the textbook in the middle of A20, they give you the formula that looks like this. X and y can switch places. It depends on which is the major axis. Because in a hyperbola, the major axis is always going to be the positive one, and they usually write that one first. So this could be y squared minus x squared. If that's the case, then they're usually going to leave the a and the b where they are, because the a is still going to be paired with the major axis, b is still going to be paired with the minor axis. A is still the distance from the center to the end of the major axis, which is the vertex. B is still the distance from the center to the end of the minor axis. So none of that has changed. Standard form is still set equal to 1. So when I get to example number 6 and they give me this equation and I'm trying to graph it, I can look at that and go, I have an x squared and a y squared and its subtraction. That has to be a hyperbola. So I'm going to go through to put it in standard form. I'm going to divide everything by 36 so that it's set equal to 1. And then it starts looking a little more normal like it's supposed to. All right, so when it's in standard form, you'll notice that they're trying to ease me into this, so they're still not giving me any value subtracted from x or y. We'll see our shifted conics in just a couple minutes. But for right now, our center is still going to be 0, 0. What is my major axis going to be, horizontal or vertical?
Horizontal.
Horizontal. It does not matter that 9 is larger than 4. That's an ellipse. What matters is that the horizontal axis is the positive one. And in a hyperbola, the major axis is the positive one. All right, so if major is horizontal, then I can say, okay, then 4 is going to be a squared and 9 is going to be b squared. So what's a and what's b? All right, so when I go to graph this, I start very much like I would for an ellipse. I'm going to come over to my center, which in this case is 0, 0. The major axis was horizontal, and the a value was 2, so I'm going to go horizontally 2 in each direction. The minor axis was vertical, and b was 3, so I'm going to go vertically 3 in each direction. Whereas with an ellipse, I would connect those with a shape that's like an oval. With a hyperbola, I'm going to connect those with a rectangle. And the diagonals of that rectangle will be my asymptotes for my hyperbola. Neither the rectangle nor the asymptotes are part of the graph of the hyperbola. They are just guides to get me to the graph of the hyperbola, but they're not the hyperbola graph itself. To graph the actual hyperbola, we have two different branches of the hyperbola. We're going to start at a vertex. So remember, the vertex is the endpoint of the major axis. We're going to start at the vertex, and we're going to draw that branch so that it approaches the asymptote. And then I'm going to come over to the other vertex, and I'm going to draw that branch so that it approaches the asymptote. So those two branches, the things that look kind of like two parabolas, they're not, but the things that kind of look like that, that's my actual hyperbola. The rest are just guides to get me there. Now, last year you might remember we talked about degenerate conic sections. They were conic sections that, depending on the way you drew it, the graph could be an abnormal shape. For instance, if you remember, the conic sections come from slicing a double cone. So we talked about if you sliced that cone exactly where the two pieces came together. You know, typically if you slice perfectly perpendicular to the axis that runs through the center of that cone, you would get a circle. But if you just so happen to slice right at the point where those two cones come together, you're just going to get a single point. And so a single point is an example of the degenerate conic section. It's a circle degenerated down to a single point. So in the middle of page A21, they give us a degenerate hyperbola there in figure 13. And they show you that if you have x times y is equal to a constant k, you're going to get something that is a hyperbola. It's going to have the two branches in alternate quadrants. So that particular example, you had a branch in the first quadrant and a branch in the third quadrant. Some of them you would have a branch in the second and the fourth. It still is going to graph with a hyperbola, but it looks nothing like the equation of a hyperbola. It's xy is equal to a constant k. So we run into one of those on the homework on number 23, so that's why I point that out to you, that when you get to 23 and you're like, wait, this does not look like any of the equations that we've studied, it's that degenerate. And so you could go back to that. Basically, you're just going to make an XY chart and plot points to figure out which quadrants it's going to go into and to know how to sketch its graph. Okay, so what happens if we shift these conic sections that we've been working with? We actually did that with the circles. Remember that any value subtracted from x is going to be a horizontal shift, and we usually use h for that. Any value subtracted from y is going to be a vertical shift, and we usually use k for that. So when we had our equations of our circles previously, they would give me something like this, and we were saying the center is 2, 3. So we came over 2 and up 3, and then we used that as the center to count out our radius and draw our circle. In essence, what we did was we started right here at a center of 0, 0, and we horizontally shifted 2 because 2 was subtracted from x, and we vertically shifted 3 because 3 was being subtracted from y. So we've done a little bit of that shifting already. But look at example 7. Example 7 gives us a parabola that we need to shift. We've got y is equal to 2 times x minus 1 squared minus 1. All right, so when I look at that, if I pair that up with the equation of a parabola in standard form, here's something that I have to be careful with. Notice that it's x minus h, so it's like the opposite of that number, but it's plus k, so it's going to be the exact number that is sitting there. The reason for that is that 1 is not tacked to the x, so it could actually be moved to the other side and grouped with the y, right? So if I moved this k over to the other side, it would be y minus k, and so then that fits our rules, right? Any value subtracted from x, any value subtracted from y. It's just that we typically write it over here, and so that's why it's a positive k over here. Okay, so looking at this guy, what would my center be for this parabola? What's h? 1. What's k? Negative 1. Good. So my center is going to be 1, negative 1. Which way does this open? Up, down, left, or right from what we studied yesterday? It's going to open up, right? Because we've got y is equal to a positive x squared. Okay? So that's how we know that it's opening up. That is all that I get from that standard form. Yeah, that 2 out in front, if we remember the ideas of stretching and shrinking when we have that factor of 2 out in front, it's going to make it a little taller and narrower. But that's all that I get. I get the 2, I get that it's positive so it opens up, and I get the vertex. Now, they suggest to me in the textbook that if that exact same example was not given to me in standard form, if it was given to me in ax squared plus bx plus c form, they tell me that I need to complete the square to get it in standard form. I disagree with that. I can get the exact same 3 pieces of information without having to take all the time to go through completing the square. And when I'm on an AP exam where every second counts, I do not have time to waste time doing something if there's a faster, easier way to get that information. So I could look at this problem in this form and get the same information from A that I did over here. I could get the 2 that would tell me that it had the stretch factor, and I could get the y equals a positive x squared, so I knew it was opening up. So really the only other thing that I would need would be the vertex. So when I'm in this form, remember that you can get your vertex by doing negative b over 2a to get the x value. And then, of course, once you know an x, you can always just plug in to find a y. So if I did negative b over 2a, my b value is negative 4, and my a value is positive 2. So that would give me positive 4 over 4, which would be 1. Once I know that x is equal to 1, then I can use direct substitution and plug that in, and I'll get my y value of -1. So I have the exact same 3 pieces of information, and I did not have to go through completing the square to put it in its standard form to get that. Okay? So whichever form they give it to me, I can get what I need. All right, so look at the last one. For our last example, they start off with an equation that I have to first figure out what I'm working with. Am I working with a circle, a parabola, an ellipse, a hyperbola, so that I know what to do with it? Okay? So when I look at the equation that they give me, I've got 25x plus 2 squared plus 4y squared is equal to 100. Is that a parabola? No. How do you know? It has x squared and y squared. A parabola has one or the other, right? Is it a hyperbola? How do you know? It's addition, not subtraction. So that takes me down to either ellipse or circle. How do I tell the difference? Yes, when I'm working with a circle, these coefficients would have to be the same. So it would either have to be 25 and 25 or 4 and 4, because you have to be able to divide through and get an equal radius all the way around for a circle, right? So because those numbers are different, I know that I'm working with an ellipse. If I'm working with an ellipse, it's got to be in standard form set equal to 1. So that I'm going to go through to begin with and divide everything by 25. And then it starts looking like it's supposed to. But that's how I could look at it if it were given to me in this form and know where to start. Okay? So once it's in this form, I know I'm working with an ellipse. What's my center? -2, 0. Perfect. -2 subtracted from x, 0 subtracted from y. Which is the major axis, horizontal or vertical? Vertical, because it is the larger one with an ellipse. So that means that this is going to be my a squared and this is going to be my b squared. So what's a? And what's b? All right, so I'm going to go to my center of -2, 0. You told me major axis was vertical and a was 5. So from that center, I'm going to go out 5 to the end of my major axis, my vertex, and out 5 to the end of the major axis, my vertex. B then is the distance from the center to the end of the minor axis. So I'll start here and I'll go 2 right and left to the endpoints of my minor axis. And then, of course, with an ellipse, I do make an oval out of it. And that's all that we want from it, is just to generate the graph. All right, so here is our homework for tonight. And remember that 23 was the one that we talked about that was that degenerate conic section. If you want to put a little star by that one to remind yourself to, you could use the middle of page A21 as a guide with that, but basically you're going to make an XY chart for that one. It's not going to look like the rest of them do.